Hey guys, welcome. Yeah, so our second additional example in L'Hopital's rule. And if we try to evaluate the limit as is, this is what we're going to find. Because remember, as x goes to infinity, tan inverse of x squared is going to go to pi over 2. So inside the parentheses, we're going to get pi over 2 minus pi over 2, which is 0. So we'll get the infinity times 0 situation. But wait, we cannot apply L'Hopital's rule in the infinity times 0 situation. We can only apply L'Hopital's rule in the form 0 over 0 or infinity over infinity. But a mere rewriting of the original question here is going to allow us to get the 0 over 0 indeterminate form. And here's how we rewrite the original question, like this. Because dividing by 1 over x squared is the same as multiplying by x squared. So this here is a mere rewriting of the original question. Now, as x goes to infinity, in the numerator we'll get pi over 2 minus pi over 2, which is 0. And in the denominator, as x goes to infinity, 1 over x squared is going to go to 0. So we get the 0 over 0 situation. So what I'm saying is that we should look at this as being in the form f of x over g of x, limit as x goes to infinity, where f of x is tan inverse of x squared minus pi over 2, and g of x is 1 over x squared. Since we found that the limit as x goes to infinity of f of x over g of x is 0 over 0, L'Hopital's rule would tell us that we can instead take the limit as x goes to infinity of f prime of x divided by g prime of x. And so that means this original question, which is the same as this and therefore that, is equal to limit as x goes to infinity of f prime, which is right there, divided by g prime. Remember, f was tan inverse of x squared minus pi over 2, and the derivative of tan inverse of x squared is 1 over 1 plus x squared squared times 2x by chain rule, minus the derivative of pi over 2 is 0, so I didn't bother writing minus 0 in the numerator. And then for this denominator, g of x, to find g prime, just rewrite g of x as x to the negative 2 power, and then the derivative will have to be negative 2x to the negative 3, which is the same as negative 2 divided by x cubed, right? Okay, cool. Now, if we simplify this a little bit, we see that what we have here, and I need an equal sign, so here's my equal sign. What we have here, which is this here, right, where all I've done is just put this 2x where it belongs right there. Yeah, what we have here, we could rewrite like this, right? We can turn it into multiplication by the reciprocal of the fraction we're dividing by, right? We're dividing a fraction by another fraction, and so we could instead say times the reciprocal of the second fraction, right? Okay, cool. That's all I've done. Now, notice that this x here and this x cubed are going to turn into x to the 4th. And this 2 here will cancel that too, but there's a minus sign from this 2 in the denominator, so the minus sign we're going to throw on the numerator. So in the numerator we'll have negative x to the 4th, and then the denominator is 1 plus x to the 4th. And we still have limit as x goes to infinity, right? Okay, cool. So we could rewrite the denominator 1 plus x to the 4th as x to the 4th plus 1. Easy enough to gather, right? Now it makes it very easy to see that as x goes to infinity, this plus 1 in the denominator has negligible contribution, and this fraction or this quotient is going to be dominated by x to the 4th over x to the 4th, which is 1, but then we have a negative in the numerator, so this limit is going to be negative 1. Yeah? All right, cool. And therefore, the original limit question will also have value negative 1 by L'Hopital's rule. Yeah, cool. All right. If I find anything very interesting on L'Hopital's, I'll make another video. But otherwise, between the first so many examples I gave you and these two additionals, it should be sufficient. Yeah. All right. Cool. Keep watching and take care.